And the whole purpose of this talk is actually going to be to enable you guys to write your own transceivers, right? So it's very important that nobody feels like they're left behind. If there's stuff you want to ask, go ahead. And if we can't finish the whole presentation in time, then so be it. I'd rather have everyone sort of be on the same page as me than sort of go over the slide too fast. So just very quickly, what about myself? I mean, I already gave the introduction to the whole track. If you find a guy called Braun online, that's me. So again, if you have the most common name in the universe, you have to sort of fiddle around with the characters. I've been contributing to GNU Radio for a couple of years now, and I did that mainly while I was at the Cultural Institute of Technology, where I also got my PhD. I've recently graduated and now a full-time developer for EDA's research.
Congratulations.
Thanks. Okay, so I've kind of split this into two parts, and first of all I'd like to talk about how to build PHYs using OFDM. And the whole point of this part is that you should be able to make PHYs without actually knowing all the details. Like say you come from the computer science end and you know lots about link layer stuff and Macs like Andre was talking about, and then you sort of just need something to connect your devices over the air, then I'd like to make this process as easy as possible for you guys, okay? So, and I mean, I don't know if this is kind of like one of our favorite comics at the lab. There are some issues, and I hope that I can sort of point out the most important ones today. Okay, just very quickly, when I'm talking about OFDM, what does that even mean? It stands for orthogonal frequency division multiplexing, and it's just a way to get lots of data over the air. So I mean, there's all kinds of ways we can do that, and OFDM has kind of become very popular. It's used in pretty much every standard nowadays, and this might get too far into details, but I just want to sort of put this in here. What we do is we transmit data on different frequencies at the same time. And so if you have a look at this picture here, you can sort of this is a time frequency diagram. And basically we have complex symbols that represent bits. That's the common way how we operate in digital communications. And sort of you can see these complex symbols, they're sort of spread out in time and frequency. And if you don't know what complex symbols are, just imagine have a look at this. You take bits, in this case you take 2 bits and then you map them onto a complex number. And this picture was copied straight out of the 802.11 standard. So this is all very, very real stuff that I'm talking about, okay? And when I talk about OFDM symbols, I'm talking about symbols transmitted at the same time. When I'm talking about subcarriers, I'm talking about this narrowband transmission on one frequency. When I'm talking about a frame, that's like a set of OFDM symbols. And if you this is sort of kind of a textbook representation of an OFDM transmitter. So I guess there should be an arrow here that says something like bits. We map bits to complex symbols, and we have this IFT operation, which for reasons I don't want to explain here, do this frequency division, multiplexing. Between symbols, we add a guard time, which we call cyclic prefix, and from here on it's just your standard transmitter path. Okay. So question is, how can we implement all of this in GNU Radio? And there's one idea. For example, Wi-Fi uses OFDM, but it doesn't use fixed packet lengths, right? So you have MTUs of different sizes, or say you're SSHing over Wi-Fi and you use the push flag a lot. You might be sending out very short packets, and then you download something, you get longer packets. And this is kind of something if you have your standard flow architecture, then it can be a bit difficult to implement something like this, because you don't have states in the GNU Radio flow graph, and we can't sort of do if and then wait for this and then do something else. But it's all possible. I'm going to show you how. Okay, there's one core feature of GNU Radio that's sort of still quite new, and I'd like to reiterate on that before I go into the actual presentation. They're called tagged stream blocks. Now, give me a hands up. Who actually knows sort of what GNU Radio does? It's Oh, who doesn't? That's more important, actually.
You don't know?
Like, just like has actually, you know, an idea about sort of how the radio program works. So like, this is kind of what Tom had open earlier. So these rectangles I would call blocks, and we put data into a block, and then it gets processed, something happens, and these arrows represent sort of the connections or the buffers between these blocks. And we can sort of, like, imagine we have a sound card, input, and then we put that into a filter, and you can sort of imagine that, like, data going through all the time. But when we're handling packets, like, this can be a bit awkward, so we introduce this concept of tagged stream blocks, and these are blocks that operate really exactly like other blocks, but they understand the concept of a packet boundary. So we have like a set number of items that go into this block, and then the block knows that this is the first and this is the last item. And imagine like a filter, sort of, you can't sort of filter like continuously because you'd have like overlap between packets, and this is something we got rid of with this concept. And there's a couple of examples of tagged stream blocks that I'm going to show you. Actually, I have a demo right here. So this is, I think I'll just close the block list so we get more space. Okay, so this is a very, very simple flow graph. And it will just generate a signal, it doesn't matter what, and don't bother about this block either. But the idea is, like, when you're coming out of here, you have an infinite stream. Like, it'll just produce data all the time. And this block does the transition where it goes from one state to the other. The thing is, like, from a 10,000 feet point of view, there's not much of a difference. So all of this gets handled in the same way by the GNU Radio scheduler. But here we get an idea about how this works. And this is the reason this is true is because we have tags that denote the position. Now, I'm creating a sine wave here, but it could be anything else. It could be bits. And what you can see here, like these little triangles, are actually tags that denote the beginning of a packet. So if we zoom into this here, like you can just see, like, this is the start of a packet and this is the start of the next packet. In between we have something, doesn't matter what. And I'm actually using the like the trigger feature here to trigger on these tags. So when I'm sort of visualizing data, I can actually sort of plot it, sort of always starts at the packet boundary. And if you have a look at this output, this sort of gives me, it prints a tag, and a tag is a kind of additional metadata that we can sort of attach to a specific item. And you'll see, like, every, I'm not quite sure, like every time there's a packet starts, like, we'll get one of these outputs. Oh yeah, every 128th item is a packet marker. Okay, so this is just something I really needed to talk about before I get into this. Now, first of all, there's kind of two sets of OFDM codes, and like what I'm talking about here all depends on the new set of codes, which are, like, if you have a look at these files, in case you're having a look at this later on the video, these are all that use these new elements, because we introduced a couple of new features in GNU Radio which are all used by these blocks, and there's also kind of an old state where we didn't have these features yet. Okay? And one thing that I always wanted when I was sort of working on this is I wanted it to be truly parameterizable. So I have this, like, GNU Radio flow graph, and it does OFDM, and I want to be able to give it sort of like a configuration that does, for example, Wi-Fi, then change the configuration, and then it does something else entirely, like DRM or DAB, for example. So this is sort of the idea. And there should be, like, sensible boundaries between logical processing steps, so you can add your visualization and instrumentation steps anywhere in the flow graph and debug graphically, what Tom talked about earlier. So let's have a look at the transmitter. And the transmitter is available as an example in GNU Radio Companion. Oh dear, this is going to be a bit awkward. Okay, so, and you can see that it's comprised of lots of different steps. So it basically finishes here, but I've got them all listed up just in case there's not enough space. And it starts off with a CRC block, which is obviously not part of the OFDM transmission, but we just need that in case, we always need that, because we need some way to verify at the receiver that we've been receiving good stuff. And the reason I'm highlighting this is because it's already one of these tagged stream blocks I mentioned earlier. Because, as I said, we want to put in any length of packet, and then what it will do is add 4 bytes of CRC at the end, and then output a new packet which is 4 bytes longer than the input. And that's why it needs to understand these boundaries, because otherwise it wouldn't know where to put the CRC itself. And then if we go through to the next step, we will actually see this is the payload. This is what we want to transmit, and this actually gets split up. And in the top path, we have a block called packet header generator, which calculates a header. Now, this is very configurable, because if we have a look at it in the flow graph, like I'm just going to double click this to show you the configuration, you can see there's actually an object which we pass to the block. So the block has a conceptual idea of what it does, but how it's actually done is implemented somewhere else. And so there's a thing called a header formatter, and this exists in my flow graph as well, up here. And you can see this is just like something we generate from our Python code. So like I'm creating a OFDM packet header generator, giving it some information about what I want to do. And then if I go back to the flow graph, this takes, on the one side, this object which generates headers. On the other side, it has a look at the payload, and then it calculates a header and outputs it on on this channel. Obviously, we also need to transport the payload itself. I mean, that's kind of obvious. So if data comes in here, then we always have 8 bits per byte, which is, this is not going to be suitable later on. You'll see why. So we sort of need to unpack this. And then we have 2 streams. Like this is bits which correspond to the header, bits that correspond to the payload. Yeah, so obvious. And this is sort of the next step. So we have these 2 channels. And here we map the bits to complex symbol. That's what I was mentioning earlier. An interesting thing here is, like, we can use any kind of modulator on both of these paths. I mean, they can be different ones, and they are actually in this example. So this enables us to use different modulations on the header and on the payload. And we could even, exchange one of these blocks for something completely fancy and do some weird. I mean, OFDM has all of these special modulations that affect the signal properties, and we can sort of just change one of these blocks. And that's the nice thing about this architecture, is that if there's this one component we want to change, there's no weird dependencies, which means that like blocks and left and right get affected. We can just change one of these blocks. So we have strict boundaries of what happens. After this, we have complex symbols, we don't care what they are, and the next processing block will always do the right thing. And in this case, we have a multiplexer which still understands these packet boundaries. And that's also important because, as I said, they'll probably be different length. So this guy has a look at what's coming in and sort of does the right thing at the output. And the actual transmitter, this is actually it. This is all there is. First of all, we have to distribute the complex symbols in the right way in the time frequency plane. And this is also where we add pilot symbols. Now, if you don't know how digital communications over the air work, like we're transmitting unknown data, so the receiver's job is to figure out what was transmitted. But we have to sometimes transmit stuff that the receiver already knows it's going to be there to sort of give it a clue what happened over the air. And then we have an FFT, which is, and this is also very nice about the whole thing. The FFT does not care about packet boundaries. And it doesn't have to. Like, it just takes one OFDM symbol, does its thing, and then takes the next one. So these tagged stream blocks and the non-tagged stream blocks, they interoperate. That's a pretty cool feature. Cyclic prefixer, it just adds the guard interval I was talking about earlier. And also roll-off, I'm going to talk about that later. Now, this is kind of the problem that we had earlier. I mean, with older versions of the OFDM code. Now, this is the time frequency plane, and anything that's white can occupy payload data. Now, as I said before, like we also need to transmit pilot symbols, and they could be anywhere. So in Wi-Fi, it kind of looks like this. We have sort of a header, and then we transmit pilot symbols on the same frequency all the time. And then digital broadcasting standards, they do something like this, where they sort of distribute the pilot symbols. And sort of this needs to be configurable. And this is an example of where I just change parameters and it'll do the right thing. So this is a Python vector, actually a tuple. I assume you know what I'm talking about. And we just denote the position of pilot symbols by indices. And in this case, we only have 2 subcarriers which transport these pilot symbols, so this is actually enough. In this case, we sort of have to give it a list, and we sort of represent it like this. So in the first OFDM symbol, we have pilots here and here, then it's empty, which is why this is empty, and so on and so on. And of course, we can sort of add headers, that kind of stuff. Okay. Receiver. The receiver is kind of the same in inverse, but it has like there was one problem that we sort of were facing, and this is, you know, when we're receiving, we're just getting samples from the antenna, and then eventually there'll be a packet, and we sort of have to figure out how long it is, and maybe even what kind of modulation we're using, and how we do that. Because, as I said before, we don't have states in GNU Radio. We can't do like if, whatever, then, and there's this block called the header payload demuxer, which solves this problem. So it takes like the signal as an input, and it also takes a trigger signal. Sort of someone else has to figure out when a packet starts. And it sort of, so we get the data, and then eventually we'll get a signal. Okay, this is a packet, and then this block sort of wakes up. Until then, it'll discard everything. It'll sort of put the whole, and then it sort of just takes the header, because that's going to tell us about the rest. Send that to some other processing path, and wait for a result. And when we know some metadata about the actual payload, then we can sort of send the payload to the next demod state. And this is how we do kind of, it's not really a state machine or something, although there's actually a state machine inside this, but it's just like a, like the output of one path will depend on the input of another. Okay, so when we get the header, which is always a fixed length, I mean, anything else wouldn't make sense. And even if you had variable header length, then you could just like take the first part of the header and sort of to figure out the rest, and then do the same thing twice. And then you just go the inverse steps of a OFDM receiver. And I don't want to go into the details because it's pretty much the same as before, except for we have to figure out how the channel modified the transmit signal, so equalization, estimation. But this guy is interesting. This is like eventually we'll get the same bits that we transmitted on the header side. And here we have the header parser, and this is exactly the inverse function to the header generator I explained earlier. And the interesting thing is, if we have a look at this, this actually takes the same object that we had before. So this is my flow graph, and this was my head. No, sorry, this is the header formatter object. It's called header formatter. And this example actually also contains a receive chain, so you can play around with it. And if I have a look at the receiver, I just put the, I actually didn't put the header formatter in here because it defaults to the right values, but I'd be using the same object. And that's, I mean, in practice, you're not going to use the same object because the receiver and the transmitter don't run on the same machine, but you have the same configuration. Okay, so like to reiterate, header payload demuxer takes care of this pseudo-stateful problem. So we get the data, we also get like someone tells us when the packet starts, we evaluate the header, and then we can transmit the payload. Okay, so this is where it all gets interesting, and fingers crossed, I hope everything will work fine. Okay, so wait a minute. Right. So this is what's the time? Oh, okay, I've got this one. Fine. So before we have a look at the whole thing, I just want to show something about how tagged streams work while I'm running demos anyway. So this is what happens. Like I'm just transmitting random data. And this block will just limit my flow graph. It sort of stops the block. I go back from one domain to the other, so I'm just going to packetize 100 bytes into one packet, but just by definition, and then calculate the CRC. And so if I run this, okay, I'm sorry about the formatting, but you can see it's actually pretty small. Okay, so this is the data before we have the CRC, and you can see like every 100th item we get a new packet, and afterwards, like it's every 104th item because we've added the CRC. Now, if I did something like this, I'd just be streaming data directly into this block. I get an error message like this, missing length tag. We get that a lot on the mailing list, which is why I wanted to bring it up here now. So you can pipe tagged streams, aka packets, into blocks that don't understand this concept, but you can't do it the other way around, okay? And it'll just crash and give you this error. Okay, so this is the receiver chain, and what I kind of skipped over a bit earlier was this part. So I have this upper part of my flow graph which will actually detect packets, okay? And we just use an algorithm that's called Schmidt and Cox because the way we set up the header is suitable for this kind. And I don't want to go into the signal processing details here, but just imagine that this guy will find the beginning of a packet, and it'll sort of output a high signal on this lane and input it to the trigger. And then we also do some other stuff, but eventually we'll still get samples that were received from my USRP device and pipe them into the same block. And then down here, this is what I was going on earlier. Like this will sort of transmit things between two different receiver flow graphs, or subflow graphs, I guess you could say. Now, if you have a look at this is my the part of my flow graph that decodes the header. Like you can see, there's something going on here because suddenly we get these dotted lines, right? And this is because what we have here is actually a feedback loop, but it's not exactly a feedback loop which you sort of think of when you know control engineering. This is asynchronous. Like this is just a message, okay? So if you know if you know what an IIR filter is, it has a feedback loop, and we can't implement these directly in GNU Radio flow graphs. We can put them in blocks, that's fine, it'll all work, but we can't do real feedback loops. But this is different because this block can wait until it receives the message. Like we can just do it asynchronously. There's no reason to stay within strict timing here. Okay. So that's how the receiver works. Is any questions up to here? None? Okay, cool. So I've provided all of these examples in the actual GNU Radio tree, like GR Digital /examples. You'll find all of these. And lots of people, they say, okay, that's easy. I'm just going to grab these, start transmitting. Now. I'm sorry? Yeah. I hope they don't do it this way, though, because... and I've gotten about 10 different people asking me the same question, and it's always the same. What they do is like this, and okay, I guess the name of this flow graph kind of gives away what will happen. So... First of all of the OFDM transmitter and receiver, they've been packed into hierarchical blocks. And if you start experimenting, use these. Don't go ahead and try and connect all these subcomponents yourself. First get this running, and then you can try experimenting on the rest. So, yeah. So here's the OFDM transmitter. I'm going to transmit whatever. I don't care. In this case, I'm actually resampling. This is just to adapt sampling rates and dump them into my device. Actually, I'd like to just go a step back before I run this and tell you about my setup. So this is a USRP B210. Like if you want to ask me details about the specs, I'm happy to do that later. Right now, if you don't know what this is a transceiver board. It's the kind of thing you sort of probably start working on, I guess, if you're sort of getting into the whole subject. And very popular devices at the moment. I'm not going to unplug it, but this is sort of the antenna to a RTL SDR dongle, which is plugged into my USB. You can get them for, they're pretty cheap. I don't know, like $20? Okay. So I used this for this example because I wanted to like show you that you don't need the most expensive stuff to get this all running. Unless you could do it like this. So, first of all, I have the receiver here. I'm gonna get it going. Okay, nothing going on because I'm not transmitting. I'm gonna start the transmitter, and if it works, then we'll see data coming in here. Well, actually, we're gonna see it down here. Okay, I should have tried this beforehand. Now I have to.
Now you have to fix it.
Oh no, I don't have to fix it. I just have to wait. Okay. Transmitter is running. Receiver sees nothing. Actually, it sees nothing at all. that's not good. Crap. Wait a minute. I shouldn't have rented out my. I shouldn't have given Silva my laptop because I wanted to. Wait a minute. Where's my receiver? Here it is. Is this? Oh, this is actually probably using the. No, okay, Silvan, can you help me with this?
Yeah, it's not finding the RTL. You gotta.
All right, yeah, but why not? All right, there it is. Okay. Nice. Whew. Well, I did say it wouldn't work, right? So, okay, start the transmitter. Okay, something's going on. But we're not receiving any data. Okay, so, any ideas? No.
Can you?
It's not about the size, man.
Average the FFT.
Sure. Rappa. Yeah, what I'm going to do here is I'm going to close this transmitter, receiver. I'm going to leave the transmitter running and start my. Oh, come on. Sorry.
You probably need to restart it.
Yeah, I just realized.
That's why it didn't work the first time.
Okay, so I'm just gonna tell you what the answer is. Like this is kind of going the right way, but if I'd have started the transmitter after the receiver, you would have seen like a huge increase of noise floor here. And what I did wrong was, well, I mean I did it right because I wanted to show you what I did wrong is, like I'm piping the output of this straight into the USRP sync. And the reason this is a problem is, like I'm just going to restart the transmitter.
You can auto scale.
All right, yeah. Thanks. So, you see these amplitude values? Tom mentioned earlier, stay between -1 and 1, okay? I'm going way over the top. This is super this is clipping. Like this is not going to work, and this is what most people do wrong. So, okay, please. Just gonna. You can see here that I'm actually reducing the amplitude by a lot. And where's my? That's much more like it. Okay, so we get a nice OFDM spectrum. Like it's very. I mean, this is really clear. Like this is a super signal to noise ratio. But when you start playing around, like this is what you're aiming for. Okay. So let's start the receiver again. Okay, I don't think I can run these guys at the same time.
Yeah, one of them taking over the bus.
Yeah. Okay, so here you can see like all these tags. This is actually from the receive side, so I'm actually receiving packets now. And like the payload I was sending was actually a RAM signal. So this is just like some bullshit. I mean, sometimes it's useful to transmit a payload that you can plot just to make sure that you're getting the right thing. So this is the actual receiver working fine. Fantastic. Okay. So first step, make sure you actually get a nice spectrum at the receiver, and you'll be fine. So couple of hints. So OFDM has this problem that we call the peak to average power ratio, which is why we get this clipping thing. So with other modulations, it's actually not quite as difficult. Play around with the gains on both the transceiver side, and in doubt, like go back to the gain. Actually, reduce gain on both sides. It'll help you with your linearity. There's a feature called roll-off. You can set it in the hierarchical block. Yeah, I'm not going to explain what it does, but it helps reduce the out-of-band radiation. Okay, so like if you want to get this perfect rectangular shape, then you need to set this to a non-zero value. But if you set it to 0, you'll still be able to receive with this kind of setup. Okay, so like in WX GUI, aim for something like this. And you don't need these massive signal-to-noise ratios, but what you do need is like the shape, okay? So in this demo that I was just demonstrating, I'm using 250 kilohertz of bandwidth, which isn't much. QPSK modulation, if you sort of do the math, you get like 375 kilobits. But that's like the maximum value. It's always less than that because like I'm not accounting for headers, and if you add forward error correction, which I'm not doing here, then it'll still go down. But let's run the whole thing again, just to give you an idea about what's like current work. So this is the receiver transmitter that actually works. There we go. We're receiving something, and now we're just gonna have a look at my CPU usage. And I mean, for a low bandwidth transmission, this is actually occupying a lot of my cores. Okay, so I mean, obviously, I'm running both the transmitter and the receiver, and I also know that most of the CPU power is going into the synchronization block because that has to run all the time. And I'm currently working on a like a hardware accelerated detector that uses Folk that Tom talked about, and that's going to help a lot to reduce this. Okay. Oh, yeah, I'm just going to leave this. Where are we? Oh, too many windows. Okay. So the big question is like, I mean, you can use this out of the box, as I showed you. Like, just think about the gain values and stuff, and it'll hopefully work. But if you want to do your own stuff, what do you do? So, as I said, like try and use the blocks as much as you can, because a lot of debugging and thought has gone into these, and like eventually you might have to change one of them, or add new ones. But when you sort of start playing around, like I recommend going this way. First of all, synchronization and detection is very specific to the actual protocol. So what I'm doing here, it could work for Wi-Fi type signals, but then if you have digital broadcast signals, for example, it will not. Then you need your own detection and synchronization algorithm. But you can have a look at the examples, like what's already in there, and sort of write something that gives the same output, but just uses different DSP algorithms in the background. The header format is also like something you'll have to change, but we've tried to make that as easy as possible. So this is yeah. Can you guys read that? No. Okay, this is. Doesn't really matter. I'll just like this is probably a bit easier to read, but I snipped out the irrelevant part. So this is the the base class for a header block. Okay, and what you do is you override this class and add your own info. So basically, these are the two most important methods you'll have to override, overload: the header formatter and the header parser. And like, it's really simple setup. You it needs to know the packet length. It needs an output buffer where it can write the bits, and it'll operate on this vector of tags, and the tags is the metadata. And you sort of write stuff into the tags, but you can also read from the tags if there's stuff in there that was used previously. And the parser, as I mentioned before, is in the same method because they can share code. And it's the same thing. Like, it has an input buffer which it sort of reads from, and then it puts stuff into these tags. Really straightforward. Like, there's nothing you need to know about GNU Radio to do that. You just like override it, and then you need to create one of these blocks and throw them into the packet header generator and parser, and then you'll have your functionality available.
You mean packet length is the size of the header. It's not the size of the complete screen.
So the size of the header is, as I said, fixed. So you
Is that packet header?
wait a minute.
Packet
Where's my
header length?
Here's my
That's actually the
constructor.
header, so that's not
He's got header length as one of the methods.
5 lines down.
Yeah. Okay. So you can. This is the constructor call, and the header length is actually part of this, and it'll sort of. Well, you can't see it here, but it'll be one of the attributes of this block. Okay. And you can query that, and I think you can even change it. No, you can't. But you shouldn't do that in a running while your flow graph is running anyway. Okay. You don't look satisfied. Do you have more questions, or?
Well, the packet header here is not the packet that you're going to send over here, or am I wrong here?
So you'll get information. You'll get information about the payload,
Yeah.
and then from that you calculate the header.
Yeah.
Okay. And give it back to the flow graph. Right. Like, any more questions? Just bring them up. Like, it's much easier to discuss it while I've got this on screen than it is later. Okay. Oh, okay. So. Right. Okay. So, no, seriously, are there any more questions about this whole thing?
Are you using, probably a little bit too technical, are you using
Don't worry.
iterative implementation of Spindle and Cox?
Are we using any others?
Iterative version. And I don't.
No.
Your say Spindle and Cox is taking almost of the processing power there?
Yeah.
There's a very fast implementation of it. It shouldn't be.
Yeah. Now, this implementation, like I was just demonstrating, is actually like, if I pull it up in control port, you see the problem in the what's it called, performance monitor. It's actually a hierarchical block that
That's my next question.
yeah.
Is how much overhead is from the.
It's like in most of I think a lot of the processing is actually going into buffers and coordination, and yeah.
And then the next question was about the granularity. So, if you're going to do this again, I know you benefit from having the small grain blocks, in that you can switch them and you can use different algorithms quite easily. But do you think it's worth it?
Yes, I do. Absolutely.
Okay.
Very much so. Because, I mean, you can always... that's the big question of software radios. Granularity versus, monolithic implementation. Yeah. So, but, for example, I'm just going to close these. So, if I have a look at this is the whole receiver flow graph. Like, I can add instrumentation blocks at any point. Yeah. So, for example, this is my equalizer. And the output of the equalizer should give me blocks, complex symbols that already look like my like the constellation diagram I'm aiming for. So say I'm not like say the header the header parser is giving me faulty data, then I have all the tools of GNU Radio to debug this, and like the frame equalizer has the same concept as the packet header generator, is that the actual DSP algorithm is actually not in the block itself, and you can change the DSP algorithm by passing a different objects. Now, it can be difficult to debug this in a standalone thing, because like we have all the QA infrastructure in GNU Radio. So we could just write a QA C++ file, but that's not really easy because you need to create test data, and then you have like these huge lists of complex numbers that you're sort of copying pasting into your C file, and it's just really annoying. And this is so much easier because you can just like give it noisy data and then see if the output is correct. I mean, I don't even mind doing this right now, like because this is something I'm pretty confident will even work. So.
Except with the special tag keys.
Oh yeah, yeah, that's fine. I'm actually a typo in here. Whoops, there. So where is it? I'll need a GUI constellation. So I can just like drop it in here. Does this do vector lengths?
Yeah. No, you have to do a stream, vector stream.
Oh, I just do it here. It doesn't matter. So right, and I think I need to change this to. Oh wait a minute! I need to do the WX because I already have syncs in here. Constellation sync. No, I need a scope sync, right?
Working on soon. Yeah, but you want scope sync, yeah.
Right. So, and this is like for learning about OFDM and stuff. This is absolutely invaluable because you can like check every single point in time, like everything like this. But in terms of performance, you might have a trade-off. I mean, you have a trade-off, obviously, yeah.
So it's a general thought on kind of software radios in general. I love the fact that you can do that and put in your instrumentation where you want with a visual interface. But there is an argument that if you were working directly with code, it'd be easier. So if you had a visualization class and you just work in the code, it might be easier than. It's a trade-off.
Yeah, I think this is actually in terms of development time. This is pretty good.
Sure.
Like I mean, as I showed earlier, like it'll like my cores are pretty busy at the moment, right? So that's the big problem you have. Okay, this is a QPSK thing. This equalizers actually doesn't output soft states. If you know what I'm talking about, so you get like this square thing. So this is already the correct output.
How do you actually extract a single subcarrier there?
Okay.
It's actually not. That's all subcarriers being serialized.
Yeah. So.
Okay. So you can't.
You can see like the difference of color here and here.
Yeah.
Like dark blue means I'm operating on vectors, and in this case, one vector is always one OFDM symbol. So you get like the time frequency plane. You operate on that. Eventually, you'll need some block that knows where the actual payload data is and sort of picks it out, and that's what the serializer does. And if you have a look at the configuration, like you get this variable, yeah, and you can see it just like gives me a list of carriers.
You could misuse this and just put one of them there.
Yeah, for example, yeah. And that's what I like about this modular approach. Like say, like you could do fancy stuff like use different modulations on different subcarriers, and then you can like just add two of these like at the end of this, like pick out the ones that you.
It's just because I made just what to do this, like extract an element of a vector. I can send it.
Right, and that's what I like about this modular approach, and also like very. Like what I mentioned earlier, that this sort of enforces like logical boundaries. Like once you leave the, where is it? So, sort of once you leave the complex domain and go back to bits, like there's nothing here that cares about where they were beforehand, right? And that's really important because you can sort of, debug different components individually and so on.
One more question: can you actually run the performance monitor to show us? Like, where's the?
Only if it's actually in there. Wait a minute.
Yeah, it depends on if you compile.
I don't. Sorry, I don't have any. Like, I'd have to.
Maybe in the end.
Yeah. Okay. Exactly. Yeah. Okay. But it's like you wouldn't see much because it'd be a huge cloud of millions of blocks doing stuff. Because this is.
But you can use this bar plot.
Wait, that's the performance monitor. Yeah, but you still have lots and lots of blocks, and then.
Yeah, but maybe there's one peak, and you can.
Yeah, but it doesn't give you a true reading of your actual because like the scheduling overhead is taking over the actual processing overhead because you have so many blocks. Okay, so but if you and we have no way of accumulating that. That would be interesting if you could sort of like put all the information from one hierarchical block into the like combine it in the performance monitor. Okay, I think I'm going too far into specifics. Okay, yeah. So right. So next question is like how do we do max with this? Because like maybe you care about the file layer, but maybe you just want something that actually works, and then you want to implement your own max on top of that. Okay. And the problem is, if you think in terms of PHYs, then this continuous streaming API, this is what you actually want. Like if you work on PHYs, then you know all about filters and modulators, and then like stuff streaming in and out of blocks is what that's your bread and butter. Macs are different. Like you usually operate on PDUs, and you sort of handle them packet-wise, one at a time, and you have really like different problems. You have like this packet, and it needs to be transmitted at this time on this frequency. Don't care how. But say you're experimenting with Macs, like you just need that to work, right? And there's a kind of bit of a dichotomy between these two areas. So how do we solve this? Now, what we need here are what we call messages or asynchronous operations in GNU Radio. So you remember like the dotted line in the header payload demultiplexer? This actually already uses this feature for a different reason, but it's actually really designed to be able to run your own Macs. Now this flow graph, I have it open here. I close this. Thank you very much. Whoops. So I'm actually like going between these boundaries, like PDUs streaming back and forth in this flow graph. So dotted lines mean PDUs. Straight lines mean synchronous samples. Okay. So imagine I had something generating packets, and then I need to pass them to the file layer, and then stuff happens, and it gets transmitted, received, and then we sort of eventually go back to the MAC layer. And we have all these sort of message testing blocks in GNU Radio that do all these things, and if I run it, then you'll see the following stuff. So I have two blocks that generate messages at different intervals. So there's one that generates a vector of zeros, and this is sort of output here. And there's another one that just sends the message test, which is like, you can see it going up. And they're running at different rates. So imagine like the test thing could be a control signal. Like say, okay, like tune to different frequency or power down your transmitter or something like that. And obviously the vector of zeros would be the data that needs to be transmitted. And this is how we operate asynchronously in GNU Radio. Now, what you always need to do to operate on Macs is like you need to be able to handle metadata, right? It's like information about your information. And this works in both domains. Like we can, like in here it doesn't matter, like it's all the same, but we can also handle metadata on the file layer. It's possible. And what metadata are there that are actually important in GNU Radio? And if we have a look at GRUHD documentation, which is the part of GNU Radio that speaks to my user P, like we know there's a couple of tags that have special meanings. And very interesting are in this case RX time, TX time, because they control the actual timing, okay? So the header payload demultiplexer can also understand these tags and any other tags. Well, so it seems it's actually not that hard to go ahead and start playing around. So first of all, transceivers, is that a problem? Not at all. Like this would be a valid GNU Radio flow graph. Like we have a source and a sink. They may even be the same device. Like we can do half duplex with the same antenna. Like this is what happens here. And yeah, I'm just gonna this is sort of a flow graph that would have an OFDM transmitter on the one hand, and the one side, and a receiver on the other. So no, this is the one I wanted. Sorry. So this is sort of this is sort of a pseudo Mac. It'll produce packets one at a time. And if I start the receiver again, this is running out of space here. Oh, I think my device is being occupied again. But the point is that I'm transmitting like non-continuously now, so I can send out packets, and the receiver will pick them up. There they are. So okay, so yeah, have a look at this window down here, and you can see it's sort of counting out packets. This is the sequence number, synchronous. They come in like one at a second, and in between, both receiver transmitter aren't really working.
You're sending some bursts.
Yeah, exactly. So this is yeah, okay. So I'm pretty much done anyway. So this is something I should have. Okay, so I can also do that, like write an application that does this. So with my, that's right. I'm just gonna start a receiver here, and a transmitter on this side. That's right. So I can just like type stuff in here. Hi, sup, and so and this is sort of what the receiver sees. He gets like the message is decoded, but I also get metadata about my packet. So I have like packet number 0, nice. It's the first one. I was lucky. Like sometimes they obviously don't get through because of bit failures, and then the CRC won't pass and won't see anything. The thing is, if I'm not using a RTL-SDR dongle but a USRP for receiver, then I can simply I'll see the receive time here. And if I want to implement something like a back-off mechanism, CSMA, CA or something like that, easy peasy. Like it's really simple. So, like the easiest possible Mac would look like something like this. Okay, I guess you can't read that. So this is pseudocode. Like this won't actually do anything, but it's still valid Python code. I just ripped out everything that wouldn't get my point across. So this is a GNU Radio block, and it sort of has these ports where you can like put in the asynchronous data, and it'll also come out. So this is like a block that'll talk to the file layer and to a layer above. So the layer above would call this function, like give it the data, and then this Mac will figure out when to transmit the actual time, attach it as metadata to the transmit signal, and then pass it downwards to the file layer. And the same goes on the receive side. So the file layer will know about the input port, which sort of operates inside this function, and it'll pass it a message. The message contains metadata and the actual receive data. So this needs to be evaluated somehow, and then we can send this to the next layer. Okay? Because I'm running out of time here, but that's fine. Like this is kind of stuff. Like if you want to know specifics, details, and want to hack around with this, that's what we reserved the last hour for. So what I'm trying to bring across here is that using these message ports, implementing these things are really, really simple. Okay. Yeah. Okay. So exactly 1 hour after I started. Right. I think there's time for one more question because it's 40 minutes past. But I'll be around. Like you can, and if you can't find me here, you can find me on the mailing list or in GNU Radio on Freenode. Okay.
And you selling something while you do?
I don't have any for sale right now. But if you want to know about them, just ask me.
That's what he was talking about. That's part of the channel.
That might be garbage, right?
I think the problem is because it's hierarchical. Yeah, it doesn't really conform to the copies right now. And so kind of the summation of all
Do you have some for sale or not?
No, not yet. I mean, you can buy them online.
Yeah, but it's a problem with UCS when you order somewhere to get delivered.
Just quickly, what's the transmit power of the USRP now?
So it's spec'd at 20 dBms, but you have to be careful because you have to know what you're doing because
Yeah, of course, there is regulation and there is, I know. The question was mostly, so 20 dBms. Nice.
I'm not 100% sure for this device, but I think it is like it's.
How expensive are these?
Do you offer any discount to Fosdem attendees?
Sorry?
Do you offer any discounts for Fosdem attendees?
The regular price is already has the discount right now. This one is 900, but there's like a cheaper one. This is like my more capable.
Well, about the
This is a regular.
about the packet detection scheme, have you considered using the cyclic prefix to do correlation to detect the beginning of a packet?
Well, that's kind of what we do, yeah.
You know, because okay.
But there's also a fixed block in GNU Radio that can do correlation.
Sorry.
Hab ich alles?
Who are you actually?
I'm cool.
What about from KIT?
Yes.
Ah, okay. Yes.
No.
I also didn't know more than you, so.
Okay.
I'm just from the mailing list. I'm from Innsbruck. At the moment, I'm in Innsbruck, but we'll move to Braun soon. And you are, one of you is currently doing Erasmus in Poland?
No, Johannes.
Another KIT guy? I'm getting confused. Yeah, where did you get the hoodies from?
Well, they're pre-release. We're testing, stress testing them. It's alpha release. The hoodies.
Shirts. Definitely want one of those.
Everyone has better slides than you do.
You want some?
Thanks. Sorry? Es liegt ja nicht am Laptop, müsste an der Kiste da liegen, oder? Warte mal.
You know what the resolution is at the moment? You're using GB 1024.768.
Yes. I mean, it's really shitty resolution. But
We discuss this later. Like, I don't want to like cut into.
don't know about the resolution, but it should be 1024 times 768. So.
Kannst du anfangen?
Ja, irgendwie der Antrag gemeint, das Bild ist nicht drauf. Ja, egal. Ah, da. Es flackert auf jeden Fall übelst rum, wenn man hier dran langt, ne? Ne.